Good afternoon, everyone. It's my pleasure to open the last session of today's talk. Let me introduce our speaker, Nour Khoudari, and she is a graduate candidate in Temple University in the program of Applied Math. She's working with Professor Benjamin Siebold. She's also a member in the energy team of Circles. Today, she's going to talk about balancing simplicity and accuracy in field models. So Nour, you can, whenever you're ready, you can start.
Yeah. Thank you, Shashan, and thank you for all the organizers. So before starting, I would like to say that this is a collaborative work of the Circles Energy team, including Kenneth Butts from Toyota, Benjamin Seibel from Temple, Rabi Ramadan, who was previously at Temple, Solomon Al-Matroudi, and Joy Carpio from UC Berkeley. So our goal is to develop models for typical vehicle types that are accurate yet simple and instantaneous in time. And one could argue, why do we actually need such models when we have high fidelity softwares like autonomy that would take a specific vehicle type and very accurately model it with many details, which is nice, but this level of details and granularity is not relevant if we simply want to study the fuel impact of traffic at large. And whenever we are talking about modeling, there's always this debate between simplicity and accuracy and which one should be sacrificed. So in this work, we establish an energy model reduction pipeline from autonomy, which is complex and costly, but very accurate. So we take it as our ground truth, and we use it as a validation for our models. Two simplified models, which are instantaneous in time and very computationally simple. And most importantly, they satisfy clear convexity properties needed for optimization purposes. And to elaborate a little bit more about that last point, autonomy has different classes of vehicles, and each class contains like different, let's say, different model years. But autonomy gives you one function for the fuel consumption. Actually, a fuel consumption graph for an average vehicle representing each class. As you can see in the plot on the left, the blue plot where you have like the sharp edges, and those sharp edges are happening at gear shifting. Now, what we want is we want to replace that by a convex function, something similar to the red function that you see here. So in order to reach that, we could first try to take the average over all the vehicles in that class. So we average the fuel consumption of all the vehicles in that class. So we get something similar to the thing on the right, which is a more smooth curve that is smeared, but is still not convex. And whenever we have non-convexity, either in the sharp sense or in the smooth sense, we are actually creating local minima. And that's not good, because whenever you are optimizing and you have local minima, you might get trapped in those local minima while trying to accelerate. And because it's more natural to accelerate in a uniform way, this stresses the importance of having convex models. Okay, so now to have an overview of our energy model reduction pipeline, we start, as we said, with autonomy, which is a software from Argonne Labs, and it models energy based on velocity, acceleration, and some other force profiles, like, let's say, wind or inclined roads. And then it gives you a time-dependent fuel function, so it's not instantaneous in time. Next, the vehicle is exposed to a virtual chassis dyno, which is similar to the real dyno you can see in the picture with the yellow car down here. And in our case, the car is virtually exposed using like running autonomy to certain loads to get a gear by gear assessment of fuel rate versus speed and torque. Now, this data that you get is fitted and then used in a semi-principled framework to get a fuel rate function that is instantaneous in time, and you get something similar to the plot you see down here, which is a function of acceleration and velocity. But as you can see, you have like some kinks and some jumps. Now, to have an additional step of simplicity further than that, we could take this map and then fit this map with some polynomial fits, and we get a simplified model, which is more smooth, and you can see the plot of a map of the simplified model on the right. So now that we have our methodology, we can apply that to concrete 7 model vehicles that are listed down here. And to quantify the accuracy of our models, we validate against autonomy on different drive cycles. And we target to roughly have a 4% error. So our error should be within 4%. That's the target. Now, going back to the pipeline and zooming in, this is how autonomy looks like from the inside. We start by the generation of the vehicle Simulink model for the chassis dyno operation. We choose a vehicle template that is cloned and modified accordingly. Then we run that using EPA test cycles to generate baseline data needed to obtain the virtual dyno data. And then comes the dyno setup, where the virtual vehicle is exposed, as we said, gear by gear to controlled cycles of prescribed speed and torque, which is translated on the level of the dyno as supplying virtual forces. And that virtual force could be seen as, let's say, a profile of the accelerator pedal or a profile of the vehicle speed. And once we apply this virtual force, we can measure and extract fuel rate, which you can see in the 4th plot to the left, along with also extracting other metrics and quantities. So now that we have so much data recorded for each vehicle, for each gear separately, and that data is stored, we need to be, so we need some like criteria to assemble this data under certain circumstances. The simplest scenario is to choose the gear with the minimum fuel rate, but that's not resembling reality, especially at low speeds when vehicles are accelerating from standing still. That's why we implement an automated tuning routine that determines criteria like gear shifting and fuel cuts, and then those parameters are used to get more coherent maps. And now that we have our parameters and maps ready, we can implement the semi-principled model. So the idea behind the semi-principled model is to have a fuel consumption rate as a direct function of instantaneous inputs, and those inputs are vehicle speed, acceleration, and road grade. And the outputs of our semi-principled model are engine speed, engine torque, fuel consumption, gear choice, transmission output speed, wheel force, wheel power, and feasibility of the given acceleration with respect to engine speed and engine torque. Now, the reason why it's called semi-principled is because it's based on 2 parts. The physics-based part, where we are using like physics-related quantities like vehicle mass, road load coefficients, gear ratios, tire diameter, and so on. And you can see an example from the semi-principled model where we actually used those quantities. So we used those, we used the vehicle mass and some road load coefficients to calculate the wheel force and the wheel power. Now, the second part is maps from the virtual chassis dyno part. where we are using maps vehicle speed to engine speed, vehicle speed and wheel force to engine torque, and engine speed and engine torque to fuel rate. And those maps are fitted and then used. Next, we have our semi-principled model yielding this fuel consumption plot to the left. And we can fit that, as we said, with some polynomials leading to a simplified model that you see to the right. Now, it should be noted that those results are actually from an older version of our implementation of the semi-principled model and the simplified model. And we have made so much improvement since then, as you can see on the following slide. So on the left, you see the older version of the the simplified model. And on the right, you can see a newer version. And one important difference between the two versions is this region over here, where we have a cusp due to an assumption that we actually imposed on the torque converter bypass clutch, where we assumed that, for simplicity actually, we assumed that it is locked in all gears, and that resulted in under predictions, as you can see, in fuel rate at lower gears, because that does not actually reflect reality. Because in lower gears, torque converter is open in order to facilitate the vehicle launch and to mitigate the driveline vibrations. So in this newer version, we forced the converter bypass clutch to be open only in first gear. And we got better results for lower speeds. However, for the rest of this presentation, I will be continuing with results from the older version because one, the newer version is still in progress, and two, it's always good to check the accuracy of the older models that still we know have margins to be improved. Now, the polynomial that we used for the simplified models is actually of this form. So it's a cubic polynomial in V. And the reason behind that is, although we are doing fits based on data, we stop at the cubic term because if we do a physics-based model of constant driving behavior, so we're assuming that acceleration and road grade are both equal to 0, then from the physics-based model, we know that the model should be cubic in velocity. And we also assume, or we also enforce that the coefficients C0, C1, C2, and C3 are non-negative so that we ensure that we have convexity in our models. And next, we try to validate our models by first comparing the semi-principled model and the simplified model, as you can see on the top right and top left. And on the bottom left, that's the difference between the semi-principled model and the simplified model. And you can see the largest differences are actually on the jumps, which is reasonable. And at the bottom right, you can see in red, the profiles of the drive cycles that we are using to validate in the VA space. Now we could also compare autonomy's output to the outputs of our semi-principled model and the simplified models on different drive cycles. And as you can see in this bar graph, you can see the results for the mid-size SUV for different drive cycles, and the aggregate error for all the drive cycles is good on average, while the highest error is scored for this third drive cycle, showing that not all drive cycles are actually good to validate for all vehicles, because some drive cycles are actually aggressive in acceleration, and that does not suit all vehicle types. And finally, on this slide, we show model errors for all 7 vehicles that we have implemented. And those errors are computed on appropriate drive cycles for each vehicle type. And the results are all, as you can see, within 4% error. So again, it should be noted that we are currently working on further improvements. So new and hopefully better results are coming soon. And finally, some take-home messages. So this work presented a systematic energy model reduction pipeline from autonomy's high-fidelity software to simplified energy models. It was carried through 7 different vehicle types, and the simplified energy models were fast to compute, instantaneous in time, and they satisfied convexity properties without losing so much accuracy compared to autonomy. So that's it from my side. I would be happy to take any questions.
Thank you, Nour, for this good presentation. I do have one question myself, so let me ask it first, and then we'll see someone else. Yeah. So I know you proposed 3 models. One is the semi-principal model, and the other one is a simplified polynomial model, and then there is a newer version. So I know, like you mentioned, like the velocity raised to the power of 3 for the polynomial model. Can you explain why you stopped there, like for the order of the velocity?
Yeah, sure. So we said that we also consider like a physics-based model in order to model our energy. So if you actually take acceleration, so let's go back. If you take acceleration and road grade to be equal to 0, which means you are modeling like constant driving behavior, then this would be similar to a physics-based model, which would give you actually a cubic polynomial in V. So if you model based on physics, like based on air drag and things like that, for constant driving behavior, you would get a polynomial of degree 3 in V. That's why we stopped at V cubed. Yeah.
Okay. Is there some reason in particular you choose in the polynomial form instead of like the other formulations, like for example, sine, cosine, or exponential functions or something like that?
No, again, it's based on physics. That's why it has this form.
Okay, thank you.
Sure.
I have one question.
Yeah.
So, I mean, the whole motivation of, I believe that this work is that we need some simplified models, right?
Yeah.
So does this work require like doing any estimations of the fuel in the real time that we are looking for the simplified model?
No, so basically this simplified model says that give me a velocity, acceleration, and a road grade. I'll give you what the fuel rate, like an estimate of the fuel rate. And that's instantaneous in time. I don't need to look at the velocity and acceleration that were recorded previously for my drive. So it's just like the velocity and acceleration at this moment in time, and I'll give you the fuel rate.
Okay, so in that case, like, why do we need to sacrifice the accuracy if we can develop a complex model, given that we can have, say, really high powerful, like a supercomputer, and then we can calculate with like extremely high precision?
Okay. First, we're not sacrificing accuracy.
Okay.
So it is still is still reasonable within 4% of what autonomy gave us, which is good. And why
So-
can't we? Because we need simpler, like computationally simpler models.
Okay.
That's like a main reason. And also those models are convex,
Mhm.
which is important for optimization.
Thank you.
In fact, just to complement this statement,
Yeah,
right? So it's the fact that it is instantaneous in time rather than depending on the history or having lots of internal variables, together with the convexity that I think is really critical when you're not solving forward problems, but inverse problems, right? So if you have a given trajectory and you want to evaluate of that given trajectory, the energy, you can take autonomy and run it forward in time. But whenever you want to do optimization, like for example, in Eugene's talk, right? The energy was inside that function. It actually could be, Eugene, in it, if you're hearing, right, an interesting exercise to take one of the non-convex energy functions that we have and try to see what the reinforcement learning actually would give. Does it get trapped in some and try to exploit some of the gear switching, right, and stuff like that? That would actually be an interesting question.
Be happy to try it sometime.
Yeah, we should try it. We should talk about that because that would be really interesting to demonstrate that you rely on the energy sort of being convexified, right, and these kind of things. But the main point is, as Nour said in the beginning, right, even though it actually is for a real vehicle more energy efficient to accelerate up to just before the gear switch, stay there a little bit, and then accelerate again, this will feel completely counterintuitive to the human in the car. So it's essentially disallowed, right? But the other thing is also interpretability of the results, right? So let's say you use something that's non-convex and non-local in time, and you try to do some optimization. Let's say you have a supercomputer, right? So computational cost is not important to you. Then you get some answer, and the answer might be counterintuitive. Then finding out why becomes really difficult. So if you have simplified models, then the interpretability is something that's within the scope of actually seeing, right? Why is that? Well, that cannot be due to the energy function. And that, I think, is the main important point why you want simpler models. In fact, come to my talk at the end. I'll try to highlight some of these things.
Good.
And for everyone, I say that I remind that your talk is actually tomorrow, same time, like 5:15
Thank you.
Eastern.
This is Ken. I would also add to the fact that we need to keep in mind that we don't actually have deep knowledge of each of the vehicles we're going to be measuring on the highway. We only have general knowledge of the vehicle type. So these complex models that we're discussing depend very heavily on like the shift schedule and maybe even the amount of fuel, the weight of the fuel that's in the vehicle at that time. So we really don't have the opportunity to use and exploit those more complicated models.
Thank you for all the questions and the discussion. Do we have more questions from Nour? This way, still have 5 more minutes. Okay, so if there's no more questions, thank you, Nour, for this good presentation. And I think this is our last talk and in our last session of the day. So Amari, do you want to say something about tomorrow's?
So thank you all for participating. This was a great day, and we're starting back tomorrow at at 11 Eastern time and 8 a.m. Pacific time, and so then 5 p.m. European time. So see you tomorrow.
Okay.